ViNG, learning open world navigation with visual goals. Let's imagine we would like a robot to quickly figure out how to navigate to a desired goal after a modest amount of experience in the environment. In the absence of spatial maps or localization, how can we specify such goals for the robot? In this paper, we study navigation with an intuitive mechanism for specifying goals, where the user provides a picture of the destination. Navigation in the absence of spatial information can be extremely useful in applications where reliable spatial maps are unavailable. Some examples include contactless last mile delivery of mail or food in dense urban neighborhoods, and autonomous inspection of museums and warehouses. Let's imagine we would like a robot to assist with the task of contactless last mile delivery in an urban neighborhood. Dense neighborhoods may be unmapped or GPS denied, and it is convenient to specify delivery locations as images. Given a set of visually indicated delivery locations on the left, we demonstrate our system performing contactless mail delivery in the absence of any spatial maps. Stay tuned for more such real-world demos at the end of our video. In this work, we present visual navigation from goals, an autonomous, self-supervised navigation platform for reaching visually indicated goals in open-world environments that can learn navigational skills entirely in the real world without access to any spatial information. During training, we use previously collected experience to learn an environment-independent traversability function, as well as a relative pose predictor, which take a pair of current and goal images as inputs and learn the traversability and next waypoint respectively. During deployment, the robot builds a topological graph of its environment, whose nodes are associated with egocentric images and not coordinates in the world. This graph provides the robot with a coarse understanding of the spatial layout of the environment. At each time step, the robot infers its position on the graph and follows the best path to the goal. Three key ideas enable our system to autonomously navigate to arbitrary visual goals: pruning the topological graph for efficient planning, training with negatives to mitigate distribution shift, and using waypoints as a mid-level action space. Let's look at some qualitative results of our method. Tasked with navigating to a previously seen goal image, ViNG is able to successfully find a path to the goal and navigate to it. We also compare ViNG to two state-of-the-art methods in long-horizon navigation: SPTM, a dense topological approach, and OffSorb, a Q-learning approach, are unable to reach the specified goal. For another goal image, we see that OffSorb fails to localize the right goal, and while SPTM manages to reach the goal, ViNG takes a shorter, more direct path to the goal. Outdoor environments are subject to varying lighting conditions throughout the day. ViNG is able to navigate to a goal image that was specified at one time of day in the presence of drastic appearance changes such as lighting and clouds. Note that while the goal image is the same for the three runs, the observations from the environment are significantly different. ViNG learns to ignore this disturbance and solves the task successfully. Next, we demonstrate ViNG's ability to quickly and reliably adapt to novel environments. When ViNG is dropped in a new environment, it explores the environment in order to improve its traversability estimates and build a reliable graph. Despite being unable to reach the specified goal, ViNG gains experience and its performance increases over 20 minutes in the new environment. After about 60 minutes, it is able to successfully navigate to arbitrary user-specified goals in the new environment. We further show the ability of ViNG to generalize to two visually and physically diverse environments: tall grass and barracks. Using 1 hour of environment interaction as before, ViNG is able to generalize to a diverse set of novel environments that are significantly different from the training environment. Finally, we demonstrate the capabilities of our system using some more real-world use cases it enables. There's a pandemic, and you'd rather order in a pizza than go to a restaurant. Why have a human deliver it to you then? Presenting the ViNG Pizza Delivery Service, delivering your pizza to your doorstep using just an image of your house. Imagine you need to set up an active patrolling system for a museum or warehouse to monitor anomalies in a GPS-denied setting. ViNG can be reprogrammed to set up a landmark monitoring system using images of the landmarks and observe discrepancies using previous experience stored in the topological map. In conclusion, a combination of topological graphs, a mid-level action space, graph pruning, and robust training with negatives enables ViNG to enable visual goal reaching in unstructured environments. Thank you for watching.